All right, get ready because we're going deep on this one.
Deep dive time.
The second law of thermodynamics.
Oh, yeah. This is a big one.
You probably heard it's like this fundamental law of physics, right?
Yeah.
But honestly, after going through all this research you gave me, it's a lot weirder than they tell you in the textbook.
It really is. It's
Yeah.
way more interesting than people give it credit for.
So what is it about the second law that makes it so, I don't know, mind-blowing?
Well, to put it simply, it basically tells us the universe is kind of like slowly leaking.
Leaking.
Yeah, it's constantly losing usable energy and heading towards this state of what we call maximum entropy.
Maximum entropy.
Which basically means things tend to get more disordered over time.
Okay, so like my room.
Exactly like your room. If you never tidy up, it doesn't magically become more organized, right?
True. That's kind of depressing, though, to think the entire universe is just, like, winding down.
It might seem depressing, but it's also, like, incredibly profound.
Okay, how so?
Because this winding down, it's not just about messy rooms. It literally affects everything.
Everything.
Yeah, everything in the universe, from like the formation of stars to the evolution of life.
Wait, so you're saying the same law that explains why my room's a mess also explains how stars are born?
It is, and that's kind of what's so amazing about the second law, you know? It connects all these seemingly random things across vast scales.
That is pretty wild.
But to really appreciate how we got here, you know, how we arrived at this understanding, we kind of have to go back in time a bit.
All right, let's rewind. Back to when, like, people were still trying to figure out what heat even is.
Yeah, exactly. Imagine trying to explain something that you experience every day but you don't truly understand.
Right.
That was heat for the ancient Greeks. Some of them, like Heraclitus, he thought everything was essentially made of fire, you know, in constant motion.
Okay.
But then you have someone like Democritus, and he pictured these tiny, indivisible particles bouncing around in this void.
So they had these ideas about fire and motion. But it sounds like they were missing something, right?
Exactly. They hadn't figured out gases yet.
Oh, right.
It wasn't until the 1600s that people like Robert Boyle started doing experiments with air pressure.
Oh, like that diagram you showed me with the J-shaped tube and the mercury.
Exactly. That was huge because it showed that air, even though it's invisible, can exert force.
Okay, so now they're starting to figure out how air behaves.
Yeah.
But they still don't really know what it's made of.
Right. Boyle himself had this idea that air was like a fleece of wool made of particles with little springs between them. And then you have Descartes, who comes along and says, no, it's particles whirling around, constantly colliding.
Okay.
But even with those ideas, they didn't have the math to really describe how a whole bunch of these particles would act together.
They had the pieces, but not the full picture.
Right.
So along comes Newton.
Ah, yes, Newton.
What did he think?
He was incredibly influential, right? He proposed that fluids, like gases, were made of particles that repelled each other.
Okay.
And he even used this idea to come up with like a version of Boyle's law. But here's where it gets really interesting. In 1738, Daniel Bernoulli comes up with a model that basically nails it. The kinetic theory of heat.
Hold on. He had it figured out, like way back then.
He did.
That's over a century before it became widely accepted.
I know, Bernoulli was ahead of his time.
So what did he figure out?
Well, he described gases as tiny particles zipping around and colliding.
Just like we imagine them today.
Exactly. And get this, he even said that the intensity of heat is directly linked to how fast these particles are moving.
Wow.
You can almost see it in that diagram you sent me with all the little particles bouncing off the walls of the container.
That's pretty amazing. So why didn't everyone just, like, accept Bernoulli's idea?
Well, there was this other theory called the caloric theory that was really popular. It described heat as this fluid called caloric that flowed from hot things to cold things.
Kind of like, I don't know how we think of water flowing.
So even though Bernoulli was more accurate, people stuck with the idea of heat as a fluid.
It's kind of like how we still use Newtonian physics for everyday things.
Yeah.
Even though we know Einstein's relativity is more accurate.
Okay.
Sometimes a simpler model, even if it's not perfectly accurate, can be really useful. Plus, the caloric theory allowed scientists to develop some pretty sophisticated mathematical tools.
I see. So they were building on a foundation that wasn't quite right.
Yeah, but it was holding up for the time being.
Okay, so this whole what is heat thing is way more complicated than I realized.
Oh, absolutely. It wasn't just a straight line to the second law.
And then things get even more tangled as we enter the Industrial Revolution.
Oh, yeah.
With steam engines and factories and a whole new set of questions.
A whole new set of questions.
What were people wondering about?
The question was all about limits.
Limits.
Can we just keep making steam engines more and more efficient forever, or is there like a fundamental limit? Oh, I see. Like, are there cosmic rules governing how much energy we can get out of machines?
Exactly. And that's where Carnot comes in.
Carnot.
Yeah. He was this young French engineer, totally fascinated by steam engines.
Okay.
He wanted to figure out the theoretical limits of their power, to unlock their secrets.
Okay.
And in his book, Reflections on the Motive Power of Fire, he laid out some really groundbreaking analysis.
But wasn't he still working under the caloric theory?
He was.
So how could his work be relevant if that whole idea of heat as a fluid was wrong?
That's the amazing part. He basically sidestepped the question of what heat is.
He did.
He just focused on the flow of heat. And in doing so, he was able to derive these fundamental principles that paved the way for thermodynamics.
Wait, so he figured out how heat engines work without even knowing what heat really is?
Yeah. It's incredible.
That is pretty incredible.
And then this is what sets the stage for the emergence of the second law itself, as scientists start grappling with this whole new idea of energy conservation.
Okay, so things are really starting to heat up now.
Oh, yeah.
We've got the Industrial Revolution, steam engines pushing the limits, and Carnot laying the groundwork.
Mm-hmm.
But where does the second law actually appear? Who are the main players?
Well, that's where the story takes a dramatic turn, and we meet some of the biggest names in physics.
Okay, who?
William Thomson, who later became known as Lord Kelvin.
Lord Kelvin.
And Rudolf Clausius. They were wrestling with these huge questions about what's conserved in nature.
Okay.
And their insights would totally change the way we understand the universe.
All right, I'm ready for the next chapter. Bring on Kelvin and Clausius. But let's maybe take a quick pause, grab another cup of coffee, and then we can really dive into the second law and this whole idea of entropy.
Sounds good to me.
All right, so we're back. Last time we talked about how things were really heating up with the Industrial Revolution and those steam engines working overtime.
Yeah, and Carnot figuring out how heat flows. It was a really exciting time for science.
Totally. So where were we with the second law?
Right, so around this time, scientists are starting to realize that there's this thing, this fundamental stuff called energy.
Energy, okay.
That can, take on different forms, but can't be created or destroyed.
Right, like energy can neither be created nor destroyed, only transformed. Isn't that how it goes?
Exactly. That was like a huge shift in thinking.
Okay, so this means the caloric theory is starting to fall apart, right?
Yeah. It meant that heat wasn't some separate substance like caloric suggested. It was just another form of energy.
Okay, I see. So where do Kelvin and Clausius fit into all of this?
They were key players. William Thomson, who later became Lord Kelvin, he was all about this dynamical theory of heat.
Dynamical theory.
Yeah, he saw heat as pure motion, but at the molecular level. And get this, he even talked about the universe having this limited amount of usable energy that was constantly being, dissipated. Yeah, and he said that this would eventually lead to the heat death of the universe.
Heat death.
Eh.
That sounds pretty intense. Is that like what we talked about before with the whole universe winding down thing?
Precisely. He was basically saying that the universe is slowly running out of steam, heading towards this state where everything's evenly spread out.
So no more usable energy.
Right, and no more useful work can be done, kind of like a cosmic battery slowly draining.
Whoa, that's kind of a bleak thought.
It is, but also kind of amazing, right?
I guess, in a way.
Wait.
What about Clausius? What was his big contribution?
Rudolf Clausius, he was really good with the math, like really precise. He took Carnot's work and ran with it, formulating this more mathematically rigorous version of the second law.
Okay.
And in the process, he gave us one of the most important concepts in all of science, entropy.
Entropy, right. That's the one that always confused me.
Well, remember how we were talking about how systems tend to get more disordered over time?
Yeah, like my room?
Exactly. Well, entropy is basically a measure of that disorder.
Okay, so entropy is like a cosmic scorecard for how messy things are getting.
You got it. Clausius was basically saying that in any spontaneous process, the total entropy of the universe always increases. It's like a one-way street for disorder.
Okay, I think I'm starting to see how this all fits together now. We've got energy that's always conserved, but slowly becoming less useful, and entropy is tracking that descent into disorder.
Exactly.
But how do they actually connect all of this, like all these ideas, to those tiny particles we were talking about, the ones that are bouncing around and making up everything?
That's where the kinetic theory of gases finally comes back into play. Remember Daniel Bernoulli?
Oh, yeah, the guy who figured it all out way back in the 1700s.
Yeah, well, his ideas were kind of rediscovered and refined over time. There were a few stumbles along the way, though.
Stumbles.
Yeah, for example, John Waterston, he came up with a really accurate kinetic theory in 1846.
Okay.
But his paper got rejected by the Royal Society.
Like,
They thought it was nonsense.
oh, no, that's rough.
But the truth eventually came out, August Kronig came along and proposed this simplified model, imagining particles just moving along straight lines, like billiard balls on a grid. And then, in 1857, Rudolf Clausius, our entropy hero, he published this landmark paper.
Clausius again. This guy's everywhere.
That's like he's the Forrest Gump of thermodynamics.
Uh-huh. Right.
Anyway, in this paper, Clausius, he not only derived the relationship between pressure and molecular velocity, but he also figured out how to calculate the average speed of those molecules in different gases.
So they were figuring out how fast these invisible particles were moving just by looking at how gases behaved.
Exactly. It's pretty incredible, right?
That is pretty incredible. But there were still some doubters, right?
Of course. Christophorus, by his ballot, he was wondering, why, if these molecules were moving so fast, why didn't gases mix more quickly?
Yeah, if they're zipping around, shouldn't it all just instantly blend?
That's a good point. Clausius addressed this by introducing the idea of the mean free path.
Mean free path.
It's the average distance a molecule travels before bumping into another one.
Oh, okay, so they're not just zooming around in straight lines.
No, they're constantly bouncing off each other, which means they're actually taking a much longer, more chaotic path.
So more like stumbling through a crowded room than running across an empty field.
Perfect analogy.
So the kinetic theory is giving us this really vivid picture of what heat is on a microscopic level.
It is.
But how does this all connect back to the second law and entropy?
That's where two more giants of physics enter the stage. James Clerk, Maxwell, and Ludwig Boltzmann.
Maxwell and Boltzmann, these are like legendary names in physics.
They took the kinetic theory and developed these really powerful mathematical tools to bridge the gap between the microscopic world of particles and the macroscopic world of, things we can actually see and experience.
Okay, this is where it gets really good, right?
Absolutely.
So what did Maxwell and Boltzmann bring to the table? What were their superpowers?
Maxwell, he was amazing at visualization.
Visualization.
Yeah, he could see these complex things in his mind and then translate them into diagrams and equations. He figured out the statistical distribution of molecular velocities in a gas. We call it the Maxwell distribution.
Oh, like that bell curve you showed me. The one that shows how the speeds of the molecules are spread out.
Exactly. He showed that not all molecules are moving at the same speed, There's this whole range of speeds, some faster, some slower, all following this elegant pattern.
That's really cool.
But even with this breakthrough, Maxwell, he was also aware of the limitations of relying just on these statistical averages. He even explored this crazy idea called molecular speciation.
Molecular speciation.
Yeah, he was basically suggesting that molecules might not be perfectly identical, kind of like how biological species vary.
Whoa, that's a pretty deep thought.
It is. He was thinking about how assuming all particles are the same might be an oversimplification, and he even saw a connection between this and, believe it or not, social justice.
Social justice.
Yeah, he wondered how this assumption of identical particles might influence our ideas about, fairness and distribution.
Okay, that's really interesting. So what about Boltzmann? What was he focused on?
Boltzmann, he was obsessed with understanding entropy in this, deep, fundamental way.
Okay.
He saw entropy as a measure of how many different possible microscopic arrangements a system could have.
Wait, so entropy is not just about disorder, but about all the different ways you can arrange things.
Yeah, exactly. Think of it like a deck of cards. There are so many ways you can arrange the cards and still have a deck of cards, right?
Right.
But if you want a specific order, like ace to king, there's only one way to arrange them. So a shuffled deck has high entropy, tons of possible arrangements, but a perfectly ordered deck has low entropy.
Okay, I see. So a messy room has higher entropy than a tidy room because there are more ways to arrange the mess.
Exactly. And Boltzmann, he developed these amazing mathematical tools to describe how these microscopic arrangements connect to the macroscopic properties we see. He even tried to derive the second law itself just from the mechanics of those tiny particles.
So he wanted to show that the second law wasn't just some random rule, but that it emerged naturally from how atoms and molecules behave.
That was his goal. But his attempts to prove the second law led to some pretty heated debates and some mind-bending paradoxes.
Paradoxes, like loopholes in the second law.
Exactly. They really question whether entropy can always increase or if maybe there are exceptions to the rule.
Okay, now I'm really curious.
I know, right?
Paradoxes, loopholes in the second law. This is getting good, but we'll have to save those for next time.
Eh.
Okay, so last time we were just getting to the good stuff. The paradoxes that challenged Boltzmann's ideas about entropy.
Oh, yeah, the paradoxes. Those are really fun.
So tell me about them. Like, what were these paradoxes all about?
Well, let's start with Loschmidt's reversibility paradox.
Loschmidt's reversibility paradox.
Loschmidt's reversibility paradox. He basically argued that if you could reverse the velocities of all the particles in a system, it would, evolve in reverse.
Like rewinding a movie.
Exactly. And this would lead to a decrease in entropy, which, seems to violate the second law.
Right, because the second law says entropy always increases.
Yeah.
So if we could just hit rewind on the universe, we'd see everything becoming more ordered.
That's what it seems like, right? But Boltzmann had a pretty clever counter-argument. He said that while reversing velocities is theoretically possible, the initial conditions needed for entropy to actually decrease are, incredibly improbable.
Okay, so what do you mean by initial conditions?
Well, imagine trying to perfectly rearrange a shuffled deck of cards just by, flinging them in the air.
Oh, okay, yeah.
Not impossible, but the odds are astronomically against it.
So it's like, yeah, you could technically unmix your coffee and milk, but you would need a ridiculous amount of precision.
Exactly.
Okay, so that's Loschmidt's paradox. What about the other one? You said there was another one, right?
Yeah. Oh, yeah, we've got Ernst Zermelo, another brilliant physicist, and he brought up this thing called Poincare's recurrence theorem.
Poincare's recurrence theorem.
It's a mouthful, I know. But it basically states that in a closed system, any state will eventually repeat itself, given enough time.
Wait, so you're saying that if we just wait long enough, the universe will reset itself?
Well, in theory, yeah.
Whoa, that's trippy.
It is. And Zermelo argued that this means entropy can't always increase, because eventually it would have to decrease as the system cycles back to a previous state.
Okay, so we've got these two paradoxes that seem to be, poking holes in the second law. Did Boltzmann have an answer for this one, too?
He did. He argued that the time scales involved in Poincare's theorem are just, mind-bogglingly huge.
How huge are we talking?
Think, trillions upon trillions of years, maybe even longer.
So basically, by the time the universe resets itself, we'll all be long gone, so who cares?
Well, in a way, yeah. He was basically saying that these paradoxes were interesting, but didn't really affect the practical applications of the second law.
Okay, I see.
He even proposed this interesting idea called the fluctuation hypothesis.
Fluctuation hypothesis.
He imagined the universe as being in this state of overall equilibrium, but with these little pockets of low entropy, like ours, randomly fluctuating within this larger, higher entropy sea.
So, we're living in a bubble of order amidst cosmic chaos. That's kind of humbling.
It is. And this leads us to J. Willard Gibbs, this brilliant American physicist. He was really good at math.
Gibbs, okay. What did he do?
Well, he brought a lot of rigor to the field of statistical mechanics.
Statistical mechanics, right.
He wasn't really focused on the paradoxes. Instead, he developed this framework to really understand how entropy and the second law work in real systems.
So he was more about the nuts and bolts of how it all works.
Yeah, exactly. He came up with this idea of ensembles. They're basically collections of imaginary systems that represent all the possible states a real system could be in.
Okay.
And this allowed him to study systems statistically in a much more sophisticated way.
So instead of trying to track every single particle, he's looking at the big picture, like a probability map of all the possible arrangements.
Exactly. And Gibbs, he realized that a key assumption for the second law to work is that systems really mix thoroughly in what we call phase space.
Phase space.
It's basically a mathematical landscape that represents all the possible states a system could have.
Okay.
And this mixing is really important. It's like, shuffling that deck of cards until all the arrangements are equally likely.
Got it.
But Gibbs also pointed out that not all systems actually exhibit this mixing behavior.
They don't.
No, some systems get stuck in these simple, repetitive cycles, they never really achieve that thorough mixing.
So there are loopholes. Not everything in the universe is destined for, like, total chaos.
It seems that way. It just highlights how complex this all is, you know?
Hmm.
It's not just that everything gets messy, it's this statistical principle that emerges from how things behave on a tiny scale and how they behave on a larger scale.
Okay, that makes sense. So Gibbs helped us understand how entropy works in the real world.
He did.
But what about Maxwell's demon? We can't forget about that little guy. Where does he fit in?
Oh, Maxwell's demon. He's like a reminder that we shouldn't get too comfortable with our understanding of this stuff.
Yeah, tell me about him.
So imagine this tiny being, right? This demon, who can control this little door between two compartments of gas.
Okay, so he's like a gatekeeper.
Yeah. And he can open and close this door to let fast-moving molecules through one way and slow-moving molecules the other way.
So he's sorting molecules by their speed.
Exactly.
Mhm.
And by doing that, he seems to be able to, like, decrease entropy, which, as we've learned, shouldn't be possible.
Right. It violates the second law.
It does. He's creating a temperature difference between the two compartments without expending any energy himself.
So it's like a loophole, right? Can this demon actually exist, or is it just a thought experiment?
Well, that's the big question, isn't it?
It is.
People have been trying to design real-world systems that mimic the demon, but the consensus seems to be that he can't truly break the second law.
Oh, okay. Why not?
Because it turns out that the information the demon needs to do his job, knowing which molecules are fast and which are slow, actually comes at a cost, and that cost preserves the second law.
So he might be clever, but he can't outsmart the universe.
Nope. But he did force us to think about, like, information and energy and entropy in new ways.
That's cool.
It really pushed the boundaries of our understanding.
So we've come a long way, haven't we? From ancient philosophers to mischievous demons.
We have.
But where does the second law stand today? Is it still as relevant as it was back then?
Absolutely. I mean, it governs everything from how we design engines to, like, how we understand the evolution of the universe. But with all the new technologies, nanotechnology, quantum computing, all that, we're constantly pushing the limits of what we know about thermodynamics.
No, the second law isn't like a finished story. It's still evolving.
Oh, yeah, absolutely. It's very much a living, breathing idea.
And that brings us to the textbooks. How has the second law been presented in textbooks over time?
That's an interesting question. Early textbooks, they often presented it as like a principle, a starting point.
Okay.
But over time, there was this shift towards portraying it as something that's been, like, proven.
Even though, as we've seen, there's still a lot of unanswered questions.
Exactly. It's understandable that textbooks try to simplify things, you know? But
Right.
this can sometimes create this false sense of certainty, like it's a done deal, you know? But as we've seen, there's still a lot we don't know about the second law.
So it's a reminder that science is always changing, always evolving.
It is. And that's what makes it so exciting. It's not just a set of facts. It's a journey.
And maybe one of our listeners will be the one to make the next big discovery about the second law, right?
Maybe. Who knows?
Well, thank you so much for joining us on this incredible deep dive into the second law of thermodynamics. It's been a wild ride.
It has.
We've explored everything from ancient philosophy to mischievous demons, the birth of steam engines, to the heat death of the universe.
It's been a lot of fun.
I hope you've come away with a newfound appreciation for this amazing law that shapes our understanding of the cosmos. And who knows, maybe it'll even inspire you to explore some of these mysteries yourself.
The universe is full of wonders waiting to be discovered.
That's right. Thanks for listening.